Embark on a daring quest to unearth's hidden history. What if an advanced civilization thrived millions of years before humanity, leaving behind only the faintest whispers in the geological record? Imagine a world ancient beyond comprehension, where intelligent beings built, innovated, and perhaps even perished long before our earliest ancestors walked upright. This isn't science fiction. It's a profound scientific thought experiment known as the Silurian Hypothesis, and it challenges everything we believe about our place in cosmic time. Could our seemingly unique reign on this planet be merely one chapter in a much grander, far more ancient story? The implications are paradigm-shifting, redefining not just human history, but our very understanding of intelligence in the cosmos. If you're ready to unravel this earth-shattering mystery and explore a possibility that could redefine our origins, then like and subscribe to embark on this incredible journey with us. Our planet, a vibrant tapestry of life and geological processes, holds secrets far deeper than we often imagine. We tend to view human civilization as a singular, unprecedented event, the pinnacle of Earth's biological and technological evolution. But what if this perspective is profoundly limited? What if the geological strata beneath our feet conceal the remnants of an intelligence that predates us by epochs, by eons even? This is the arresting premise of the Silurian Hypothesis, a captivating idea first formally presented in 2018 by scientists Gavin Schmidt, a climatologist at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester. Their paper, published in the esteemed journal Icarus, wasn't about finding definitive proof of a lost society. Instead, it was a rigorous exploration of a crucial question. If an advanced, industrial civilization had existed on Earth tens or hundreds of millions of years ago, what evidence might remain today, and how would we even begin to look for it? The very notion of a primeval intelligence challenges our anthropocentric view of history. We are accustomed to thinking of the past in terms of archaeological digs unearthing Roman ruins or ancient Egyptian pyramids. Our historical records stretch back a few millennia, our understanding of hominid evolution a few million years. But Earth's timeline is vast, stretching over 4.5 billion years. The Silurian period, for which the hypothesis is playfully named, a nod to the Doctor Who villain, the Silurians, a reptilian race said to have existed on Earth millions of years ago, occurred roughly 443 to 419 million years ago. While the hypothesis isn't strictly limited to this specific geological period, it uses the immense scale of deep time to underscore the almost unfathomable intervals involved. If an industrious society existed, say, 60 million years ago, around the time of the Paleocene-Eocene thermal maximum, a dramatic period of global warming, what traces would endure?
The challenge lies in the relentless, transformative power of geological processes. Earth is a dynamic planet, constantly recycling its crust. Tectonic plates collide, uplift, and subduct, burying ancient surfaces deep into the mantle where they melt and are reabsorbed. Erosion, weathering, volcanism, these forces conspire to erase all but the most robust evidence over vast spans of time. Imagine a modern city with its skyscrapers, concrete jungles, and intricate infrastructure. What would remain of it after, say, 50 million years of relentless geological assault? Concrete would crumble, steel would rust away, and even plastic would eventually degrade. Any intricate machinery would be pulverized into dust, its metallic components oxidized and dispersed. The geological record is like a shredder, constantly tearing apart and reassembling the pages of Earth's history. This inherent difficulty in preservation is central to the hypothesis. Schmidt and Frank weren't claiming that a lost society did exist. Instead, they recognized that our inability to find evidence isn't necessarily proof of absence. It's an acknowledgement of the profound limitations of our current methods when peering into such deep time. Consider the fossil record. It's incredibly sparse, a mere snapshot of life's immense diversity. We've identified only a tiny fraction of the species that have ever lived, and even fewer of those have left behind recognizable fossils. If the preservation of biological organisms is so rare, how much rarer would be the preservation of ephemeral technological artifacts? A complex machine, unlike a bone or a shell, is not designed for geological endurance. The hypothesis forces us to reconsider the very nature of evidence. We're not looking for obvious ruins. We're searching for something far more subtle, technosignatures. These are not traditional fossils, but rather indirect indicators of technological activity. Think of the chemical fingerprints left behind by an industrial civilization. Our own civilization, for instance, is leaving a distinct mark on Earth's geology in the form of elevated carbon dioxide levels, plastic pollution, rare earth element deposits from electronics, and even novel radionuclides from nuclear activity. If a primeval intelligence existed, it too would have left its own unique signature, albeit one now incredibly diluted and altered by the passage of geological eons. The quest then becomes one of deciphering these faint, buried whispers. Could it be that we are looking for the wrong things, or simply in the wrong places? The very act of asking the question opens up a new frontier in scientific inquiry. It encourages us to look at the geological record with a fresh perspective, not just for the story of life, but potentially for the echoes of a lost intelligence. It bridges the gap between traditional geology and astrobiology, forcing us to consider how we might detect intelligence not just on distant exoplanets, but potentially right here, beneath our own feet. The journey to understand the Silurian hypothesis is a journey into the profound depths of geological time, a daring intellectual adventure into the unknown. It compels us to confront our assumptions about uniqueness and perhaps to find a humbler, yet more awe-inspiring place within the vast cosmic narrative. Our planet is a relentless history machine, constantly grinding, folding, and reshaping its own narrative. This dynamic nature, driven by forces like plate tectonics and erosion, poses the most significant challenge to detecting any prior sophisticated society on Earth. Imagine, curious explorers, trying to find a specific grain of sand on a beach after 1,000 tides have washed over it. Now amplify that challenge by millions of years, and you begin to grasp the scale of the problem. The Earth's crust is not a static archive, but a constantly churning cauldron, making the preservation of ephemeral signs of a lost civilization incredibly difficult, if not seemingly impossible. Let's delve deeper into this geological erasure. The Earth's surface is divided into massive tectonic plates that are in perpetual motion. These plates converge, diverge, and slide past one another. When they converge, one plate often plunges beneath another in a process called subduction, carrying vast swaths of the Earth's surface and anything on it deep into the mantle. Over tens of millions of years, an entire continent-sized area can be subducted and melted, its materials recycled back into the Earth's interior. Any remnants of a primeval intelligence, whether structures, artifacts, or even highly durable waste, would likely be pulled down into this fiery abyss, utterly transformed and obliterated by immense heat and pressure. Consider the timescale. The Silurian period, chosen as a whimsical namesake, stretches from approximately 443 to 419 million years ago. Even if a technologically advanced civilization existed much more recently, say 60 million years ago, as some speculative scenarios suggest, the forces of erosion are truly astonishing. Water, wind, ice, and biological activity relentlessly break down rocks, mountains, and any exposed surface features. A monumental structure like the pyramids of Giza, impressive as they are, would likely be reduced to a pile of dust and scattered debris over millions of years, especially without continuous human maintenance. What then of softer materials or more complex technological constructs? they would vanish without a trace. The fossil record, our primary window into deep time, beautifully illustrates this problem of preservation. Fossils are incredibly rare, forming only under very specific conditions: rapid burial, fine-grained sediment, and the absence of scavengers or decomposers. Even then, the vast majority of organisms that have ever lived have left no fossilized remains. We find fragments, glimpses, rare specimens that hint at the incredible biodiversity of the past. If the fossilization of durable biological structures like bones and shells is so hit or miss, how much more improbable is the preservation of complex technological artifacts made of materials that degrade far more quickly? Concrete, steel, silicon, these are not substances designed by nature for geological longevity. They are subject to rust, dissolution, and crushing pressures. What about something as fundamental as stratigraphy, the study of rock layers? Geologists use stratigraphy to understand the sequence of events in Earth's history, with older layers typically found beneath younger ones. However, geological processes don't always unfold neatly. Faulting can displace layers, folding can warp them, and erosion can remove entire sections, creating unconformities, gaps in the geological record where time has simply been erased. A primeval intelligence might have existed during one of these missing periods, leaving behind no contiguous record for us to easily decipher. It's like finding a book with entire chapters torn out. The story is incomplete, and vital information lost forever. Moreover, the materials that would constitute an industrial society's legacy are themselves subject to degradation. Plastics, while seemingly persistent in our modern era, eventually break down into microplastics, and over millions of years would likely be incorporated into the geologic cycle, their original form lost. Metals oxidize and corrode, becoming indistinguishable from natural mineral deposits. Even radioactive materials, while leaving an isotopic signature, decay over time, making their detection incredibly challenging after tens of millions of years. Could a lost society have developed materials with unheard-of resilience? Perhaps, but even then, the sheer scale of geological forces would test their limits. The Earth, in essence, constantly erases its own memory. This isn't a deliberate act, but a consequence of its dynamic internal and external processes. When we look at the geological record, we're seeing an edited, fragmented, and often heavily censored version of Earth's past. The challenge of the Silurian hypothesis is to determine if any subtle, indirect signatures could persist through this relentless geological blender. It's a testament to the power of our planet's natural systems and a humbling reminder of the transient nature of even the most sophisticated technological achievements when confronted with geologic eons. The question isn't just, what would they leave behind, but what could possibly survive? And the answer, often, is vanishingly little.
If direct evidence of an ancient industrial society is unlikely to survive the relentless geological recycling, what then are we looking for? The answer lies in technosignatures, indirect detectable markers of technological activity. This concept, often applied to the search for extraterrestrial intelligence, is equally relevant when peering into Earth's own deep past. We're searching for the chemical fingerprints, the subtle disturbances, or the anomalous concentrations of elements that would betray the presence of a primeval intelligence, even if its cities have crumbled to dust and its machines long since oxidized. This requires a shift in perspective, moving from traditional archaeological digs to sophisticated geochemical analyses. Our own civilization, the Anthropocene epoch in which we currently reside, is leaving a profound technosignature on the planet. We are altering the composition of the atmosphere, creating novel synthetic materials, and distributing unusual concentrations of rare earth elements across the globe. Consider the sudden spike in atmospheric carbon dioxide and methane, or the widespread presence of plastics in marine sediments and even remote ice cores. These are not naturally occurring phenomena at their current scale and represent a clear, unambiguous signal of an industrial civilization. If a prior society existed, it too would have left its mark, albeit one that has been dramatically diluted and obscured by millions of years of geological processes. One key area of focus for potential technosignatures is isotopic anomalies. Isotopes are atoms of the same element with different numbers of neutrons. Industrial processes can alter the natural ratios of isotopes in ways that rarely occur in nature. For instance, the burning of fossil fuels preferentially releases lighter carbon isotopes, 12C, into the atmosphere, shifting the global carbon isotopic ratio. A sudden, dramatic, and sustained shift in carbon isotopes in ancient sediments could, hypothetically, point to large-scale burning of fossil fuels by a primeval intelligence. Similarly, the widespread use of nuclear power or weapons would leave behind specific radioactive isotopes or their decay products, whose presence in anomalous concentrations could be a smoking gun. However, distinguishing such anthropogenic signals from natural geological events, like massive volcanic eruptions, which also release vast amounts of carbon and can cause isotopic shifts, is incredibly challenging. This is where the detective work gets truly complex.
Another category of technosignatures involves synthetic materials or highly processed compounds that are not found naturally. While it's highly improbable that recognizable plastics or pure metals would survive eons, the chemical constituents might. For example, the widespread production of concrete or other binding agents might leave behind unusual concentrations of specific elements like calcium, silicon, and aluminum in ancient sedimentary layers, in ratios not typically found in natural geological formations. Or consider the processing of rare earth elements, vital for modern electronics. If a lost society extracted and processed these elements on a large scale, their dispersal into the environment could, theoretically, leave a diffuse yet detectable signature across vast geographical areas, albeit one incredibly diluted. Beyond chemistry, what about unusual sediment layers? Could an advanced society have created landfill sites or mining waste dumps so extensive that they left a distinct, anomalous layer in the geological column? Our current waste disposal methods are creating novel geological strata, sometimes dubbed plastiglomerates, mixtures of plastic, sediment, and rock. While these might not survive millions of years intact, perhaps certain highly durable waste products or the unique mineralogy of highly processed industrial slag could persist. The challenge is that natural geological processes, such as meteor impacts or massive flood events, can also create unusual, widespread sediment layers, requiring careful discrimination. The search for technosignatures also contrasts sharply with the search for biosignatures. Biosignatures are indicators of life, such as specific organic molecules, microfossils, or distinctive isotopic ratios associated with biological processes. While life has existed on Earth for billions of years, creating a rich, though incomplete, fossil record and leaving widespread chemical evidence, a technosignature implies a level of deliberate manipulation of the environment that goes beyond mere biological existence. The scale of energy consumption, resource extraction, and waste production by an industrial civilization fundamentally alters the planet in unique ways. It's the difference between finding the fossilized remains of a forest and finding the chemical signature of widespread deforestation and subsequent industrial pollution. The sheer difficulty of detecting these subtle whispers cannot be overstated. We are looking for something that is almost certainly fragmented, diluted, and potentially masked by billions of years of Earth's own geological processes. It would require advanced analytical techniques, perhaps even technologies we haven't yet developed to precisely pinpoint these faint anomalies within the ancient rock record. This isn't a matter of simply digging in a trench and finding a lost city. It's a profound, complex, and potentially revolutionary quest for the most elusive of fingerprints left by a truly lost world. The possibility, however remote, is tantalizing and drives scientists to think more broadly about how intelligence might manifest and endure or not endure in the cosmic ballet of deep time.
To truly appreciate the scope of the Silurian hypothesis, we must first immerse ourselves in Earth's deep geological epochs. Our planet's history is not a continuous, unbroken line, but a series of dramatic acts, each defined by unique geological and biological conditions. These vast spans of time, the Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, and Cenozoic, represent a colossal canvas on which countless stories have unfolded, most of them entirely unknown to us. It's within these ancient eras that a primeval intelligence might have risen and fallen, leaving barely a ripple on the surface of geological memory. Let's begin with the period that lends its name to our hypothesis, the Silurian period, which spanned from approximately 443 to 419 million years ago. This was a time of significant evolutionary change. Life was still primarily marine, but jawed fish diversified, and crucially, plants began to colonize land extensively for the first time. The continents were arranged very differently, with a large supercontinent called Gondwana occupying much of the southern hemisphere. Seas were shallow and warm in many regions. Could an intelligent, technologically capable life form have emerged in a marine environment? Perhaps, if we expand our definition of civilization beyond land-based paradigms. However, the energy requirements for an industrial society, particularly the kind of large-scale extraction and processing we associate with technology, would be a monumental challenge in a purely aquatic setting. Still, the immense duration of the Silurian period leaves ample room for unexpected narratives. Moving forward in time, we encounter the Devonian period, 419 to 359 million years ago. Often called the Age of Fishes due to the spectacular diversification of marine life. Crucially, the first amphibians began to emerge onto land, and land plants developed true roots and leaves, forming the first forests. The Carboniferous period, 359 to 299 million years ago, saw the flourishing of vast swamp forests that would eventually become our coal deposits, the fossil fuels that power our current industrial civilization. If a previous society utilized similar energy sources, the remnants of their large-scale extraction might manifest as highly anomalous, concentrated deposits of altered carbon in ancient coal seams or oil fields, distinct from natural geological processes. The scale of such activity, however, would need to be truly immense to leave a global signature.
Then came the Permian period, 299 to 252 million years ago, which culminated in the most devastating mass extinction event in Earth's history, the Permian-Triassic extinction, often referred to as the Great Dying. This event wiped out over 90% of marine species and 70% of terrestrial vertebrate species. Such cataclysms are critical to consider when pondering a lost civilization. If a primeval intelligence existed, a mass extinction event could have been its undoing, leaving behind even fewer traces. The very geological processes that cause and follow these extinctions, such as massive volcanic eruptions like the Siberian traps associated with the Permian extinction, could further obscure or destroy any remaining evidence. The Mesozoic era, comprising the Triassic, Jurassic, and Cretaceous periods, is famously the Age of Dinosaurs. For nearly 180 million years, colossal reptiles dominated the planet. Could a technologically advanced species have coexisted with dinosaurs? It sounds like the plot of a science fiction movie, but from a purely geological perspective, the vastness of this era means there were millions of years, countless niches, and profound environmental shifts. If an intelligent species arose, thrived, and then vanished during, say, the early Triassic, the entire reign of the dinosaurs could have passed without any geological memory of that earlier intelligence being detectable by our current methods. The KPG extinction event that ended the reign of the dinosaurs 66 million years ago provides another example of a catastrophic event that would reset the geological clock and further bury or obliterate any pre-existing technosignatures. Finally, We arrive at the Cenozoic era, 66 million years ago, to the present, often called the Age of Mammals. This is the era in which our own lineage, the primates, eventually emerged and diversified. Even within this relatively recent era, from a deep time perspective, the interval between, say, 60 million years ago and the rise of humans is immense. Consider the Paleocene-Eocene thermal maximum, approximately 56 million years ago, a rapid and dramatic global warming event. Schmidt and Frank specifically used the PETM as an analog for the kind of spike in the geological record that an industrial society might leave. The PETM shows a massive, rapid injection of carbon into the atmosphere, causing global temperatures to soar. While natural explanations for the PETM are robust, the thought experiment asks, what if an event of this magnitude could be explained by a prior industrial society? The geological record of the PETM is surprisingly well preserved in some deep ocean sediments, offering a potential window to look for very subtle, high-resolution chemical anomalies. Each geological epoch presents a unique set of challenges and opportunities for detection. The deeper we go, the more fragmented and transformed the record becomes. The Earth's crust is a cosmic vault, holding secrets, but it's a vault that is constantly being rearranged and purged. Our quest is to find if any indelible mark, no matter how faint, of a truly lost society survived this relentless cosmic remodeling. The very geological act of considering these deep-time scenarios expands our understanding of possibility, forcing us to confront the profound scale of Earth's own dramatic history, and perhaps to glimpse echoes of intelligence beyond our own.
The Fermi paradox, famously articulated by physicist Enrico Fermi, asks a chilling question. If the universe is teeming with life, and intelligent life is common, then where is everybody? Why haven't we detected any definitive signs of extraterrestrial civilizations? This paradox usually applies to the vastness of space, contemplating the silence from distant star systems. But what if we were to turn the question inward, applying the spirit of the Fermi paradox to our own planet? If intelligent, technological civilizations are a recurring phenomenon in the cosmos, could one have arisen and vanished right here on Earth, long before our species emerged? This intriguing reframing of the paradox forms a core philosophical underpinning of the Silurian Hypothesis, adding a layer of dramatic existential inquiry to our scientific quest. Consider the timelines involved. Humanity's technological civilization, marked by industrialization and the widespread use of energy and complex materials, is barely 300 years old. Even if we extend this to the dawn of agriculture and settled societies, we're only talking about 10,000 to 12,000 years. This is a fleeting blink in Earth's 4.5 billion-year history. If a similar civilization had emerged, lasted for a few thousand or even 100,000 years, and then vanished, the geological record would swallow its traces whole with astonishing speed. The Earth has hosted complex multicellular life for over 500 million years. That's a staggering amount of time for multiple independent evolutionary pathways to lead to intelligence, and for multiple cycles of civilization to rise and fall. The Great Filter concept within the Fermi paradox suggests there might be significant obstacles to the emergence of long-lived, detectable civilizations. These filters could be anything from the improbable formation of life itself, to the difficulty of abiogenesis, to a catastrophic self-destruction event, or even a natural planetary cataclysm. If a primeval intelligence did exist on Earth and vanished, its demise might represent a terrestrial great filter, a barrier that any advanced society must overcome to achieve true longevity. Was it a self-inflicted wound, perhaps environmental collapse due to their own industrial activities? Or was it a natural disaster, an asteroid impact, or a supervolcano eruption so immense that it obliterated not only their society, but also almost all evidence of its existence? The implications of a terrestrial Fermi paradox are profound.
If we are not the first, it means that intelligence and even technological prowess might be a more common occurrence in planetary evolution than we assume. This could temper our sense of human uniqueness, placing us as merely one iteration in a potentially long line of intelligent species that have graced this planet. The drama of this realization is immense. It shrinks our perceived cosmic significance while simultaneously expanding the mysterious narrative of Earth itself. We would move from being the sole custodians of planetary intelligence to perhaps the inheritors of a very ancient, hidden legacy.
Furthermore, applying the Fermi paradox to Earth could offer insights into our search for life elsewhere. If technosignatures on Earth are so difficult to detect after millions of years, what does that say about our ability to detect them from exoplanets orbiting distant stars? The further away and the more ancient a potential extraterrestrial civilization, the harder its signals would be to distinguish from natural astrophysical noise. This perspective suggests a temporal great filter. The vastness of cosmic time may be just as effective at silencing intelligent signals as the vastness of cosmic space. Perhaps civilizations are fleeting, leaving behind only the most ephemeral of marks before being subsumed by geological or astrophysical processes. The very absence of obvious evidence on Earth then becomes a fascinating data point. It either suggests that intelligence is incredibly rare, arising only once in Earth's history, with us, or that any prior intelligent societies were so ephemeral, so non-impacting on a global scale, or so thoroughly erased by geological forces that they left no discernible trace. This prompts us to be more ingenious in our search, both on Earth and beyond. It pushes us to consider what truly long-term, geologically enduring technosignatures might look like. Not grand structures, but subtle chemical imbalances, unusual isotopic ratios, or highly specific mineral formations that defy natural explanation. Ultimately, the Fermi paradox, when brought home to Earth, transforms into a compelling call for deeper geological investigation. It challenges us to look at the familiar with new eyes, to question our assumptions about our place in time, and to ponder the profound mystery of why, if intelligence is a cosmic norm, we appear to be the only ones to have ever reached this level of technological advancement on our own vibrant planet. The silence from the ancient Earth could be just as deafening and just as meaningful as the silence from the stars, inviting us on an existential adventure into the very heart of our planet's hidden potential.
One of the most critical challenges in the quest for primeval technosignatures is distinguishing them from natural geological processes. Our own industrial civilization is leaving a unique, identifiable mark on the planet, an anthropogenic signature that is unprecedented in its speed and scale. But if we are to look for similar marks from a lost society, we must understand how to differentiate their hypothetical traces from the background noise of Earth's long and tumultuous natural history. This is where scientific rigor and careful analysis become paramount, transforming our adventurous speculation into a dramatic geological detective story. Our current era, sometimes termed the Anthropocene, is defined by the pervasive and dominant impact of human activities on Earth's geology and ecosystems. Think of the sudden, sharp spike in atmospheric carbon dioxide and methane concentrations, far exceeding natural fluctuations observed in ice cores spanning hundreds of thousands of years. This isn't just a slight increase, it's a dramatic, hockey stick-shaped curve that clearly points to human industrial activity, particularly the burning of fossil fuels. Similarly, the widespread dispersal of novel materials like plastics, aluminum, and concrete across the globe is leaving distinct, geologically persistent layers in modern sediments. The presence of artificial radionuclides from nuclear weapons testing in the mid-20th century creates a clear, globally synchronous marker. These are our calling cards, our unmistakable signature on Earth's deep future. Now, Imagine a primeval intelligence operating millions of years ago. What would its equivalent signature look like? The fundamental problem is that many of the potential technosignatures we might look for, like unusual carbon isotopic anomalies or sudden warming events, can also be caused by powerful natural phenomena. For example, massive volcanic eruptions, known as large igneous provinces or LIPs, can inject enormous quantities of greenhouse gases and aerosols into the atmosphere, causing dramatic climate shifts and significant isotopic perturbations. The Siberian TRAPS eruptions, associated with the Permian Triassic extinction, released enough carbon to significantly alter the global climate and chemistry. How would we distinguish a carbon spike from an ancient industrial society from one caused by a supervolcano? The answer lies in the pattern and specificity of the signature. A natural volcanic event, while massive, tends to have a particular geochemical fingerprint, specific ratios of gases, a distinctive mineralogy and ash layers, and often a relatively rapid onset and decay. An industrial civilization, on the other hand, might exhibit a more sustained, systematic alteration of the environment. For instance, the systematic extraction and processing of specific metal ores would leave behind unusual concentrations of those metals and their associated byproducts in distinct layers, potentially on a global scale. The consistent waste streams from manufacturing processes might create unique mineral assemblages not found in nature.
Consider the example of nitrogen isotopes. Human industrial activity, particularly the widespread use of nitrogen fertilizers and the burning of fossil fuels, significantly alters the global nitrogen cycle, leading to changes in the ratio of nitrogen isotopes, 15N and 14N. This is a distinct anthropogenic signature. Could an ancient civilization have left a similar mark through its agricultural practices or industrial output? The challenge is that natural biological processes also fractionate nitrogen isotopes, meaning the background noise is high and the ancient signal would be incredibly faint after millions of years of geological and biological recycling. Another area of differentiation involves complex synthetic molecules. While simple molecules might break down or be naturally produced, truly complex, non-biological synthetic compounds might leave some highly degraded but still detectable chemical residue. Think of the unique molecular structures of certain industrial lubricants or refrigerants. While the original compounds would vanish, their decomposition products might be unusual enough to stand out from natural organic matter, assuming conditions for their preservation were exceptional. This is highly speculative, as the deep time breakdown of complex molecules is rarely studied in this context. The scientific tools required to disentangle these signals are sophisticated. Isotopic analysis using mass spectrometers can measure minute variations in isotopic ratios, allowing geochemists to trace the origins of elements. Micro-X-ray fluorescence or electron microscopy can identify anomalous mineral grains or synthetic materials at a microscopic level. The key is to look for coincident anomalies across multiple indicators: a carbon isotopic shift, plus an unusual metal concentration, plus a spike in specific synthetic compounds. A single anomaly could be natural. A convergence of multiple interconnected anomalies might point to something truly extraordinary. The drama of this scientific pursuit lies in the meticulous effort to find a needle in a haystack, a whisper in a hurricane of geological time. It means approaching the geological record not just as a story of rocks and fossils, but as a potentially hidden archive of intelligence itself. The quest for distinguishing anthropogenic from primeval signatures is not about finding definitive proof, but about refining our methods, pushing the boundaries of what is detectable, and always being open to the possibility that Earth's ancient past holds secrets far more complex and paradigm-shifting than we currently dare to imagine.
When we explore the possibility of a lost society, our immediate instinct is often to look for obvious, tangible artifacts. Yet, the fossil record, Our primary lens into Earth's biological past serves as a powerful reminder of how incredibly difficult it is for anything to survive the immense stretches of geological time, let alone delicate technological constructs. The fossil record is less a comprehensive library and more a collection of scattered, often incomplete fragments, a series of tantalizing glimpses rather than a continuous narrative. This inherent fragility and incompleteness underscore why the absence of direct archaeological evidence for a primeval intelligence is far from a conclusive argument against its past existence. Consider the sheer scale of life that has existed on Earth. Scientists estimate that over 99% of all species that have ever lived are now extinct. Of those extinct species, only a minuscule fraction has left any fossilized remains. For an organism to become a fossil, a highly specific chain of events must occur. The organism must be rapidly buried after death, preventing decomposition and scavenging. It must be buried in fine-grained sediment, like mud or ash, that protects its structure, and the surrounding geological conditions must be stable enough to allow for mineralization and preservation over millions of years. Even then, many fossils are fragmentary, distorted, or only preserve soft tissues under extremely rare conditions. If the preservation of biological organisms, designed by nature with hard parts like bones and shells, is so challenging, imagine the fate of technological artifacts. A concrete building, a metallic sculpture, or a complex electronic device are not built to endure geological forces. Concrete crumbles, steel rusts, silicon chips degrade. These materials are highly susceptible to weathering, erosion, and dissolution. Over millions of years, they would be pulverized, oxidized, or broken down into their constituent elements, becoming indistinguishable from natural geological deposits. Even highly durable materials, if they existed in a lost society, would face immense pressures and temperatures if buried deep within the Earth's crust due to plate tectonics.
Take the example of soft-bodied organisms. While exceptionally rare, some ancient soft-bodied creatures have been preserved in extraordinary circumstances, such as the Burgess Shale in Canada or the Changjiang biota in China. These Lagerstätten offer fleeting windows into periods of life that would otherwise be entirely unknown. However, these are freak occurrences, not the norm. For a lost society's soft-bodied technology, its electronics, its textiles, its less durable infrastructure, similar exceptional preservation would be required, and the likelihood of such conditions applying to complex artificial structures across a global scale is vanishingly small. Furthermore, the geological record itself is prone to gaps and missing chapters. Unconformities, as mentioned before, are significant erosional surfaces or non-depositional periods that represent vast stretches of missing time in the rock record. Entire geological epochs can be erased by uplift and erosion, meaning that if a primeval intelligence flourished during such a missing interval, there would literally be no physical rock record left to search within those specific locations. It's like having a multi-volume history book where entire volumes have been lost to time. We know they existed, but their contents are gone. The bias of the fossil record also plays a role. We tend to find fossils in sedimentary rocks, often formed in ancient marine environments or lakes. Terrestrial environments, where many technological societies would likely develop, are far less conducive to long-term preservation due to higher rates of erosion and exposure. This means that even if a technological civilization left a significant footprint on land, its direct evidence would be even more ephemeral than marine life.
This recognition of the fossil record's inherent limitations is not a dismissal of the Silurian hypothesis, but rather a redirection of the search. It reinforces the need to look beyond obvious archaeological sites and instead focus on subtle, indirect geochemical anomalies or isotopic signatures. These whispers in the strata are much more likely to persist, albeit in a diluted form, than any physical artifact. The idea is that while a building might turn to dust, the unique chemical byproducts of its construction, or the industrial processes that supported it, might be preserved at a molecular level, detectable through highly sensitive analytical techniques. The silence of the fossil record, then, isn't necessarily proof of absence. It's a testament to Earth's dynamic processes and the immense passage of time. It encourages us to approach the geological archives with humility and ingenuity, understanding that the absence of a clear signal often means we need to listen more carefully, and perhaps with entirely new instruments. The dramatic implications are clear. If an ancient intelligence existed, the Earth itself is its tomb, its remnants dissolved into the very fabric of the planet, waiting for a sensitive enough ear to hear its faint, almost imperceptible echoes.
The Silurian Hypothesis, while focused on Earth's deep past, reverberates far beyond our home planet, offering profound implications for the burgeoning field of astrobiology, the study of life in the universe. If we consider the possibility of a primeval intelligence on Earth, it forces us to reevaluate our assumptions about the prevalence, detectability, and longevity of technological civilizations across the cosmos. This terrestrial thought experiment thus becomes a vital lens through which to refine our strategies for the search for extraterrestrial intelligence, bridging the gap between Earth's geological history and the vastness of the universe. A central tenet of astrobiology is the idea that the laws of physics and chemistry are universal. If life arose on Earth and evolved to intelligence, it's plausible that similar processes could unfold on other habitable planets. The Silurian Hypothesis introduces a crucial temporal dimension to this thinking. If intelligent life can rise, develop technology, and then vanish without a clear, enduring trace on its home planet over geological timescales, what does this imply for our ability to detect such civilizations light years away? Consider the timescales involved in the evolution of life on Earth. Multicellular life appeared roughly 600 million years ago. Complex, intelligent forms like mammals and birds are a relatively recent phenomenon. If the pathway to an industrial civilization is not a singular, inevitable outcome, but one of many possible evolutionary trajectories, and if such civilizations are inherently short-lived on geological timescales, then the window of detectability for an extraterrestrial civilization becomes incredibly narrow. We might be looking for brief flashes of light in an otherwise dark cosmic ocean.
This directly impacts the search for technosignatures on exoplanets. Current SETI efforts primarily focus on radio signals or laser emissions, which are transient and require intelligent communication to be ongoing. However, a growing area of astrobiology is exploring passive technosignatures, the long-term, persistent markers of industrial activity, similar to what we discussed for Earth. These could include artificial atmospheric compositions, e.g. chlorofluorocarbons, or unusually high levels of pollutants, waste heat signatures, or even the spectral fingerprints of megastructures like Dyson spheres. The Silurian Hypothesis provides a crucial reality check for these efforts. If Earth's own hypothetical lost society left such faint and ambiguous traces, how much harder would it be to detect them from across interstellar space? The light from distant exoplanets is millions of years old. By the time we observe a potential technosignature, the civilization that created it might have long since vanished. This introduces a look-back time problem. We are always observing the past, and that past might have been a very brief, fleeting moment of technological existence. The drama here is that our cosmic quest for intelligence might be inherently hampered by the universe's own relentless march of time. Furthermore, the hypothesis encourages astrobiologists to consider what constitutes a habitable planet in a new light. We often focus on the presence of liquid water, suitable temperatures, and a stable atmosphere. But what if a planet's long-term geological stability, its ability to preserve or erase the history of its intelligent inhabitants, is also a critical factor?
A planet with intense plate tectonics and rampant erosion might be less likely to retain a detectable record of past intelligence, even if it frequently develops such life. This could mean that some planets, despite being biologically vibrant, are effectively silent from an astrobiological perspective due to their geological dynamism.
The philosophical implications are profound. If Earth has hosted multiple, independent, intelligent species throughout its deep history, it would profoundly shift our understanding of our own cosmic significance. We would cease to be unique, but rather become part of a grand, recurring planetary drama. This could make the universe seem both more populated and more humbling. The very notion that intelligence might rise and fall, leaving behind only the most subtle echoes, adds a layer of beautiful melancholy to the astrobiological quest. Ultimately, the Silurian Hypothesis is a powerful tool for sharpening our astrobiological imagination. It forces us to confront the limitations of our detection methods, both on Earth and in the cosmos. It challenges us to think creatively about what forms technosignatures might take and how long they might persist. By looking inward at our own planet's deep past, we gain invaluable perspective on the grand cosmic search, realizing that the silence from distant stars might not be an absence of life, but rather a testament to the fleeting nature of technological civilizations in the face of deep time and planetary forces. Our journey to discover intelligence elsewhere might begin by understanding the hidden potential right beneath our feet.
To truly grasp the formidable challenge of detecting a primeval intelligence, we must delve deeper into the intricate dance of deep-time geological processes. These aren't just minor alterations, they are the fundamental forces that have sculpted our planet over billions of years, capable of erasing entire mountain ranges, opening and closing oceans, and effectively shredding the evidence of all but the most resilient phenomena. Understanding these processes is key to appreciating why the lack of obvious archaeological sites does not automatically invalidate the Silurian hypothesis, but rather underscores the sheer difficulty of the search. At the heart of Earth's dynamic nature is plate tectonics. The Earth's lithosphere is fragmented into several large and small tectonic plates that are in constant slow motion. This motion drives volcanism, earthquakes, and mountain building, but it also has a profound impact on the preservation of surface features. At subduction zones, where oceanic plates dive beneath continental plates, vast expanses of crust, along with any structures or materials on them, are drawn into the Earth's mantle, where they are melted and recycled. Imagine an entire continent disappearing over tens of millions of years, its history literally consumed by the planet's interior. Any remnants of a lost society in such regions would be obliterated beyond recognition. Conversely, at mid-ocean ridges, new crust is constantly being formed as magma rises from the mantle. This process, known as seafloor spreading, means that oceanic crust is continuously being created and destroyed. The oldest oceanic crust is only about 200 million years old, far younger than many of the deep time periods we're discussing. This implies that any evidence of a primeval intelligence that might have been built on or existed near oceanic crust would have long since been subducted, erasing that chapter of history. Only remnants on stable continental platforms or in exceptionally well-preserved sedimentary basins could possibly endure.
Erosion is another relentless force. Water, wind, ice, and gravity tirelessly break down and transport rock and sediment. Mountains are uplifted by tectonic forces, only to be immediately attacked by erosion, slowly but surely worn down over millions of years into plains or peniclains. Think of the Appalachian Mountains in eastern North America, once towering peaks, now much lower and rounded due to hundreds of millions of years of erosion. If a primeval intelligence built monumental structures, akin to our largest cities, they would be subject to the same processes. Concrete, steel, and other construction materials, while robust in human timescales, are incredibly fragile when confronted with the forces of geological erosion over eons. Their particles would be dispersed, carried by rivers to the oceans, and incorporated into new sedimentary layers, losing their original form and context. Sedimentation and lithification also play a complex role. While rapid burial by sediment can preserve organic remains, leading to fossils, it can also effectively bury and hide any evidence of technological activity. Over millions of years, layers of sediment accumulate, compacting and eventually turning into solid rock through a process called lithification. If an ancient city or industrial complex were buried, it would be subjected to immense pressure and heat, potentially deforming or recrystallizing any materials within it. Subsequent uplift and erosion could then expose these layers, but the original context and integrity of any artifacts would likely be long gone. Furthermore, metamorphism can completely transform rocks and their contents. If buried deep enough, rocks are subjected to intense heat and pressure, causing their minerals to recrystallize and their textures to change dramatically. A sedimentary rock containing traces of a technosignature could be metamorphosed into an entirely different rock type, obliterating the subtle chemical or structural clues we might be seeking. This makes looking for evidence in older, more metamorphosed geological formations incredibly challenging.
The cumulative effect of these deep time processes is a grand erasure. The Earth is constantly wiping its own slate clean, recycling its crust, weathering its surfaces, and transforming its internal materials. This isn't a flaw in our planet, but its fundamental nature. For a fleeting technological civilization, existing for mere thousands or hundreds of thousands of years, to leave an indelible mark across this vast, dynamic canvas is an extraordinary proposition. The Silurian Hypothesis forces us to reckon with the profound power of geological time, recognizing that the lack of readily apparent evidence is not a failure of the hypothesis, but a testament to the Earth's own unstoppable transformative forces. The true adventure lies in peering through this veil of geological time, searching for the most ephemeral of echoes. Mass extinction events are the ultimate reset buttons in Earth's history, colossal planetary traumas that profoundly reshape the course of life and, crucially for our discussion, further complicate the preservation of any evidence of a primeval intelligence. Imagine, with a sense of dramatic foreboding, a cataclysm so immense it wipes out the vast majority of life on Earth. If a technologically advanced society existed on our planet, such an event could not only have led to its demise, but also effectively erased its geological footprint, leaving behind an even more desolate and silent record for us to decipher. Over Earth's 4.5 billion-year history, there have been at least 5 major mass extinction events, often called the Big Five, and numerous smaller ones. These events are characterized by a sudden, drastic loss of biodiversity across multiple ecosystems globally. They are typically caused by extraordinary geological or extraterrestrial phenomena.
The Ordovician Silurian extinction, around 443 million years ago, for instance, was likely triggered by intense glaciation and subsequent global warming, severely impacting marine life. The late Devonian extinction, around 359 million years ago, saw the loss of many marine species, possibly due to oceanic anoxia and rapid climate shifts. Then came the devastating Permian-Triassic extinction, around 252 million years ago, the Great Dying, which, as we noted, eliminated 90% of marine species and 70% of terrestrial vertebrates. This event is strongly linked to massive volcanic eruptions in the Siberian traps, which unleashed colossal amounts of greenhouse gases and pollutants into the atmosphere. The Triassic-Jurassic extinction, around 201 million years ago, cleared the way for the dinosaurs to dominate, and most famously, the Cretaceous-Paleogene extinction, around 66 million years ago, wiped out the non-avian dinosaurs attributed primarily to a colossal asteroid impact in what is now the Yucatan Peninsula. The impact of these events on a hypothetical ancient civilization would be twofold. Firstly, the events themselves could be the very cause of their demise. An asteroid impact of KPG scale, for instance, would create global wildfires, tsunamis, and a prolonged impact winter due to dust and aerosols blocking sunlight, making survival for an advanced, complex society incredibly challenging, if not impossible. The long-term environmental collapse that follows, including ocean acidification and drastic climate shifts, would further test their resilience.
If their technological prowess wasn't enough to mitigate such a catastrophe, they would simply vanish, perhaps leaving behind only chaotic, fragmented debris. Secondly, and crucially for the Silurian hypothesis, mass extinctions act as powerful geological churners. The cataclysmic events themselves generate vast amounts of sediment, ash, and disturbed geological layers. The subsequent environmental changes, such as widespread anoxia in oceans, can alter the chemical composition of sediments in ways that might obscure any pre-existing technosignatures. The very processes that define these extinction boundaries, massive volcanism, impact events, rapid sea level changes, create a geological noise that would make it incredibly difficult to pick out the subtle, artificial signals of a lost society. It's like trying to find a specific whisper in the midst of a thunderous roar.
For example, a sudden global warming event caused by a primeval intelligence's industrial emissions might leave a carbon isotopic anomaly. But if that event coincided with a large igneous province eruption, the volcanic carbon signature could easily mask or mimic the anthropogenic one. Differentiating between natural and artificial causes for such anomalies becomes a profound challenge, demanding incredibly high-resolution geochemical analysis and careful statistical validation. The drama lies in this scientific sleuthing, trying to unravel layers of natural history to find a potentially artificial thread. The KPG boundary, formed by the asteroid impact, is an example of a relatively well-preserved, globally synchronous geological marker. It contains an iridium anomaly. Iridium is rare on Earth's surface but common in asteroids, and shocked quartz, definitive evidence of an extraterrestrial impact. Could a truly advanced ancient civilization have left a similarly globally distributed, unambiguous marker of its existence, perhaps through planet-scale terraforming or some other immense engineering feat? Even then, the chances of such a marker surviving 60 million years of geological churning are slim. Mass extinction events serve as a sobering reminder of the planet's raw, untamed power. They highlight the impermanence of even dominant life forms and ecosystems. If a primeval intelligence once walked this Earth, these great reset buttons of geological time would have not only threatened their existence, but also diligently worked to erase their memory from the very rocks beneath our feet. The Silurian hypothesis thus compels us to consider not just if they existed, but if anything they left behind could have possibly survived such profound geological violence and global environmental upheaval.
In our quest to uncover the faint whispers of a lost society, direct archaeological evidence is largely off the table due to the relentless forces of deep-time geology. Instead, our most promising tools lie in the realm of chemogeology, particularly isotopic analysis. This sophisticated technique allows scientists to read the subtle chemical fingerprints embedded within ancient rocks and sediments, potentially revealing anomalies that could only be explained by the presence of a primeval intelligence. It's like searching for a specific brand of invisible ink left on a document that has been extensively rewritten and partially destroyed. Atoms of the same element can have different numbers of neutrons. These variations are called isotopes. For example, carbon exists primarily as carbon-12 and carbon-13. The ratio of these isotopes in natural materials is remarkably consistent, but biological and industrial processes can significantly alter these ratios. This is the key. Living organisms preferentially incorporate lighter isotopes during photosynthesis. When we burn fossil fuels, which are derived from ancient organic matter, we release vast quantities of carbon-12 into the atmosphere, causing a measurable shift in the global carbon isotopic balance. This is one of the most unambiguous technosignatures of our own industrial civilization. So, if a primeval intelligence also relied on burning fossil fuels or engaged in large-scale biomass combustion, we might expect to see similar carbon isotopic anomalies in ancient sedimentary layers. A sudden, sustained negative excursion in C,
a measure of the 13C to 12C ratio, could, hypothetically, point to their activities. However, as noted previously, natural events like massive volcanic eruptions can also release vast amounts of carbon-12, making differentiation incredibly challenging. The devil, as always, is in the details. The specific magnitude, duration, and global distribution of the anomaly, and its correlation with other unusual chemical signals.
Beyond carbon, other isotopic systems offer potential clues. Oxygen isotopes, 16O, 18O, are crucial for reconstructing past climates, as their ratios in ice cores and ancient sediments reflect global temperatures and hydrological cycles. Industrial processes involving water or high temperatures could, in theory, leave subtle shifts in oxygen isotopic ratios. Similarly, nitrogen isotopes, 14N, 15N, are affected by biological processes like denitrification and by the widespread use of artificial fertilizers, a significant anthropogenic signature. Could a lost society's agriculture or industrial waste have left a comparable mark? What about the more exotic isotopes? The widespread use of nuclear technology, whether for power generation or weaponry, would leave behind very specific radioactive isotopes, e.g. plutonium-239, cesium-137, or their stable decay products. While these radioactive isotopes decay over millions of years, their stable decay products, or unusual elemental ratios, e.g. fission product signatures, might persist. For instance, the presence of certain transuranic elements, which are almost exclusively produced artificially, would be a definitive technosignature, though their longevity in the geological record is highly debatable. The challenge with isotopic analysis for deep time detection is multifold. Firstly, the signal itself would be incredibly diluted over millions of years due to geological mixing and subsequent biological activity. Imagine a drop of dye in a vast ocean. Over time, it disperses to undetectable levels. Secondly, distinguishing an artificial isotopic anomaly from a natural one is exceedingly difficult. Earth's history is replete with natural events that can cause dramatic isotopic shifts. Volcanic outgassing, methane clathrate dissociation, major changes in ocean circulation. Scientists must develop increasingly sophisticated models to rule out all natural explanations before even considering an artificial one.
Despite these hurdles, isotopic analysis remains one of the most promising avenues. It represents a subtle, chemical forensic science, attempting to piece together a narrative from microscopic clues. Geological core samples obtained from deep ocean sediments or ancient ice sheets, though ice cores rarely go back far enough, would be the primary source material. These samples offer continuous, layered records of Earth's past environment, acting as a chronological archive of chemical changes. The drama unfolds in the lab, with scientists meticulously analyzing these samples, searching for that elusive, unique chemical fingerprint that screams intelligence. This pursuit elevates the work of geochemists and isotope specialists, transforming them into detectives of deep time. They are not merely studying the Earth's natural evolution, but are armed with the tools to potentially uncover a hidden layer of history, a lost chapter written in the very atoms of our planet. The Silurian Hypothesis compels them to refine their techniques, to look for signals within the noise, and to consider the profound implications if they were to indeed find an unequivocal chemical whisper from a forgotten age.
While isotopic anomalies offer a glimpse into the chemical landscape of deep time, the field of paleontology, The study of ancient life through fossils also plays a crucial role in understanding the limitations and possibilities of detecting a lost society. The inherent gaps and challenges within the paleontological record, far from undermining the Silurian hypothesis, actually reinforce why direct evidence of a primeval intelligence is so elusive. It's a compelling reminder that the story of life on Earth is fragmented, and that even the most dominant species can vanish without leaving a clear, continuous trace. The fundamental challenge in paleontology is the incomplete nature of the fossil record. As discussed, fossilization is a rare event, and only a tiny fraction of species that have ever lived are represented by fossils. This inherent incompleteness means that vast stretches of evolutionary history remain undocumented. Whole lineages of organisms, especially those with soft bodies or living in environments not conducive to preservation, like upland terrestrial ecosystems, may have come and gone without leaving any discernible trace in the rock record. If entire biological groups can disappear without a trace, how much more likely is it for a technologically ephemeral society to vanish?
Consider the immense diversity of life that exists today, and then extrapolate backward millions of years. We are constantly discovering new fossil species, filling in gaps in our understanding of ancient ecosystems. This ongoing discovery process highlights how much remains unknown. If a primeval intelligence existed, it might have been confined to a specific geographical region that has since been subducted, eroded away, or simply has not yet been thoroughly explored paleontologically. The sheer vastness of the geological record and the Earth's surface means that even targeted searches could miss critical, localized evidence. Moreover, the quality of fossil preservation varies dramatically. Most fossils are fragmented bones, shells, or impressions. Complete skeletons, or instances of soft tissue preservation, are exceedingly rare and usually occur under exceptional circumstances. This means that even if a technological species existed, the likelihood of finding a complete skeleton, let alone recognizable tools or buildings associated with it, approaches zero over millions of years. The materials of technology, unlike the biomineralized structures of many organisms, are simply not designed for such long-term geological endurance. The evolution of intelligence itself presents a paleontological puzzle. We know that hominids, our own ancestors, have been evolving for millions of years, but the earliest evidence of stone tool use is only about 3.3 million years old. The development of complex technology, and especially industrial society, is a very recent phenomenon in the grand scheme of Earth history. This implies that if a primeval intelligence arose, the window during which it was technologically active might have been incredibly brief from a geological perspective, making its detection even more improbable. Paleontologists primarily search for the skeletal remains and trace fossils, footprints, burrows of organisms. They aren't generally equipped to identify chemical anomalies or highly degraded artificial materials.
Furthermore, paleontological surveys are inherently biased towards certain rock types and environments. Sedimentary rocks formed in ancient marine basins, lake beds, and slow-moving rivers are far more likely to preserve fossils than volcanic or metamorphic rocks, or highly erosive terrestrial environments. This means that if a lost society existed primarily in, say, mountainous regions or coastal areas that have since been subducted or heavily eroded, its paleontological record, if any existed at all, would be severely compromised. The drama here lies in the fact that we are often literally looking for ghosts in geological settings that are already difficult to read. The philosophical implication of these paleontological gaps is significant. It suggests that our understanding of Earth's past life is inherently incomplete, and that our current knowledge, while vast, is built upon a foundation of fragments. The absence of evidence in this context is not necessarily evidence of absence. It simply means that the conditions for preservation were not met, or that our methods of detection are not yet refined enough. The Silurian Hypothesis thus challenges paleontologists to think beyond the conventional scope of their field. It encourages them to consider if there are any subtle, indirect paleontological clues that could hint at an intelligent presence. Could anomalous distributions of certain elements in ancient sediments, perhaps linked to the diet or waste products of a primeval intelligence, be detectable? Could unusual patterns of environmental disturbance, difficult to explain by natural processes, be discerned through meticulous analysis of ancient ecosystems? While highly speculative, these questions push the boundaries of paleontological inquiry, inviting a new kind of adventurous exploration into Earth's deepest biological and potentially technological past. The silence from the ancient Earth is not empty. It's a profound mystery, full of unwritten chapters and unseen possibilities.
If we entertain the audacious notion of a primeval intelligence, the next logical step in our adventurous thought experiment is to ponder the nature of their hypothetical technologies. What would such a society build? What energy sources would it harness? And crucially, what kind of lasting imprints might these technologies leave on the geological record, enduring over tens or hundreds of millions of years? This isn't about designing alien machinery, but rather extrapolating from our own technological trajectory and considering the most durable and impactful signatures. The drama unfolds as we imagine the incredible feats and potential follies of a lost world. Let's begin with energy sources. Our own industrial revolution was powered first by coal, then by oil and gas, and increasingly by nuclear and renewable sources. A primeval intelligence would similarly require vast amounts of energy to sustain a technological society. If they utilized fossil fuels on a large scale as we do, this would leave the carbon isotopic anomaly we've discussed. But what if they developed entirely different, more sustainable, or even more destructive energy technologies? Perhaps they mastered geothermal energy on a planetary scale, tapping into Earth's internal heat. While direct evidence of geothermal power plants wouldn't survive, widespread and sustained manipulation of crustal heat flows might leave subtle, anomalous thermal signatures in the deeper geological record, or unusual mineral alterations in surrounding rocks. Or perhaps they developed advanced nuclear fission or fusion technologies. While nuclear waste is a massive problem for us, if they had truly sophisticated disposal methods or managed to stabilize radioactive isotopes, their legacy might be a subtle, long-term increase in specific decay products or elements associated with nuclear reactions, concentrated in unusual ways in certain deep geological formations.
What about their material science? Our civilization is defined by its widespread use of concrete, steel, plastics, and various alloys. These materials, while robust on human timescales, largely succumb to geological forces over eons. But could an ancient society have developed materials with extraordinary durability, perhaps advanced ceramics, composites, or even self-repairing nanostructures? If such materials were produced on a planetary scale and could resist weathering, erosion, and even subduction for millions of years, they might leave distinct, non-natural mineralogical signatures. The discovery of novel mineral phases or unusually high concentrations of engineered nanoparticles in ancient sediments would be a truly astounding technosignature. Consider planetary-scale engineering. Our species is already impacting the entire globe through deforestation, damming rivers, and terraforming landscapes for agriculture and urbanization. A highly advanced ancient civilization might have engaged in even more ambitious projects. Could they have built structures so massive, so integrated with the planetary crust, that their remnants might still be detectable? Think of the vast mining operations required to extract resources. These could leave behind uniquely altered landscapes, vast waste dumps, slag heaps, with unusual mineralogical compositions, or even deep boreholes that, while filled in, might still represent linear anomalies detectable through advanced seismic surveys. The drama here is imagining works on a scale that dwarf our own, yet still fall prey to the relentless churn of the Earth. What about data storage? If an ancient society developed methods to store information on incredibly resilient mediums, could any of that survive? Hypothetically, highly stable synthetic crystals, or even genetically engineered organisms, though this quickly veers into pure speculation, might encode information that could, with advanced future technology, be deciphered. However, the probability of such complex, information-rich structures surviving intact for millions of years is extremely low, pushing the boundaries of scientific credibility.
The key is not to imagine familiar technologies simply scaled up, but to think about the fundamental alterations to the planet's chemistry and geology that any advanced industrial society would inevitably leave. The conversion of energy, the extraction and processing of raw materials, the creation of waste products. These are universal hallmarks of technological activity. The trick is to identify the most durable and persistent of these marks. Ultimately, the thought experiment of hypothetical ancient technologies forces us to think more broadly about what constitutes evidence in deep time. It moves us beyond the archaeological paradigm of looking for identifiable ruins and pushes us towards a more abstract, geochemical and geochronological search for subtle anomalies. The drama is in the vastness of the unknown, the incredible possibilities of what a truly lost society might have achieved, and the humbling recognition that even their grandest achievements might have been utterly swallowed by the unfeeling, relentless march of geological time. The Silurian Hypothesis, therefore, is not merely about finding proof, but about expanding our imaginative and scientific horizons.
The Silurian Hypothesis, while a scientific thought experiment, carries profound ethical and philosophical considerations for humanity, compelling us to reflect on our own legacy on Earth and our place in the cosmic narrative. If we are not the first, what does that mean for our perceived uniqueness, our responsibility, and our future? This dramatic introspection transforms the scientific inquiry into a deeply human one, a cosmic mirror reflecting our hopes and fears. Firstly, the hypothesis challenges our anthropocentric view of history. For centuries, humanity has seen itself as the pinnacle of evolution, the sole intelligent species to grace Earth with technological prowess. Discovering a lost society would shatter this paradigm. It would necessitate a profound reevaluation of our origins, our evolutionary path, and perhaps even our destiny. The drama lies in this humbling realization. We are not alone in the past. We are part of a potentially recurring pattern. This could lead to a deeper sense of connection to the planet and its long, complex history. Understanding ourselves as inheritors of an ancient, mysterious legacy. This reevaluation naturally leads to questions about humanity's legacy on Earth. We are currently leaving an indelible mark on the geological record, from climate change and plastic pollution to widespread deforestation and mineral extraction. This impact, often termed the Anthropocene, is unprecedented in its speed and scale. If a primeval intelligence existed, and perhaps even perished due to its own environmental mismanagement, it serves as a chilling cautionary tale. It underscores the fragility of complex ecosystems and the potential for technological societies to inadvertently cause their own demise. The Silurian Hypothesis, in this sense, becomes a powerful ethical prompt. Are we doomed to repeat the mistakes of a forgotten predecessor? Are we also laying the groundwork for our own geological erasure?
The idea of a lost society also forces us to consider our responsibility towards the planet. If Earth has already fostered multiple iterations of intelligent life, then our role as stewards of this planet becomes even more poignant. We are not merely protecting our own future, but potentially safeguarding a cradle of life that has given rise to intelligence multiple times. This could instill a greater sense of urgency in addressing environmental crises, recognizing that the Earth's capacity to host complex, technologically advanced societies might not be limitless, and that past failures, or natural cataclysms, serve as stark reminders. The drama is in the weight of this responsibility, an intergenerational and even interspecies burden. Furthermore, the Silurian Hypothesis intercepts with discussions about humanity's cosmic significance. If intelligence arises and falls on a single planet without leaving a detectable, lasting signature for cosmic neighbors, it might suggest that civilizations are inherently fleeting. This could make the Fermi paradox even more perplexing, but also more profound. It hints at a universe where intelligence is common, but its duration is brief, or its detectability limited by the sheer immensity of space and time. This would challenge our aspirations for interstellar communication and long-term cosmic presence, perhaps shifting our focus from outward expansion to inward sustainability. The discovery of a lost society could also profoundly impact our cultural and societal narratives. Imagine the implications for religious beliefs, historical interpretations, and even national identities. Such a revelation would spark an unprecedented global conversation, perhaps leading to new myths, new scientific disciplines, and new philosophical movements. It would be a paradigm shift of epic proportions, forcing us to redefine what it means to be human in a potentially ancient, populated cosmos. The adventurous quest for truth would lead to a dramatic reevaluation of our very being.
Finally, the hypothesis encourages us to contemplate the very nature of progress and longevity. Is technological advancement inevitably linked to environmental degradation and self-destruction? Or can a civilization achieve a sustainable equilibrium that allows it to persist for geological timescales, leaving only benign or even beneficial technosignatures? The Silurian Hypothesis, by presenting the stark possibility of a vanished past, compels us to reflect on our own trajectory, challenging us to envision a future where humanity avoids the fate of its potential predecessors, and instead leaves a legacy of wisdom and harmonious coexistence with our ancient planet. The ethical stakes are immeasurably high, intertwining our scientific curiosity with our deepest human aspirations for a meaningful and lasting presence in the universe. The burgeoning field of comparative astrobiology offers a fascinating perspective on the Silurian Hypothesis, allowing us to leverage our nascent understanding of exoplanets and the conditions for life elsewhere to better inform our search for a primeval intelligence on Earth. By studying what we look for on distant worlds, we can refine our approach to scrutinizing our own planet's deep past. This cross-disciplinary approach transforms the solitary quest for Earth's hidden history into a grand cosmic dialogue, highlighting the universal principles that govern the rise and fall of life and intelligence.
Now, apply this thinking to Earth's past. If we were an alien civilization observing ancient Earth, how would we distinguish between natural geological phenomena and the signatures of a primeval intelligence? Comparative astrobiology emphasizes the need for multifaceted detection strategies. Just as we wouldn't rely on a single spectral line to confirm life on an exoplanet, we shouldn't rely on a single type of anomaly, e.g. a carbon spike, to confirm a lost society on Earth. We need to look for a suite of correlated signals that, in combination, are difficult to explain by natural processes alone. For example, on exoplanets, scientists are starting to consider technosignatures beyond just radio signals. These include industrial pollutants in atmospheres, such as chlorofluorocarbons, which are purely artificial, unnatural levels of greenhouse gases, or even waste heat. Applying this to Earth, we would then look for analogous signals in our geological record. Could ancient industrial pollution have left its mark in deep ocean sediments, perhaps as unusual concentrations of heavy metals or synthetic compounds? The question then becomes one of detectability after millions of years of dilution and transformation. The concept of planetary habitability itself gains new nuance. While we typically focus on the conditions necessary for life to arise and persist, comparative astrobiology, informed by the Silurian Hypothesis, asks, what conditions are necessary for a technological civilization to leave a lasting, detectable mark? A planet with intense geological activity might be great for life's evolution, but terrible for preserving the memory of its inhabitants. Conversely, a geologically quiet planet might preserve a more complete record, but perhaps be less dynamic in fostering complex life. This dramatic interplay between planetary dynamism and historical preservation is a key takeaway. Now, apply this thinking to Earth's past. If we were an alien civilization observing ancient Earth, how would we distinguish between natural geological phenomena and the signatures of a primeval intelligence? Comparative astrobiology emphasizes the need for multifaceted detection strategies. Just as we wouldn't rely on a single spectral line to confirm life on an exoplanet, we shouldn't rely on a single type of anomaly, e.g. a carbon spike, to confirm a lost society on Earth. We need to look for a suite of correlated signals that, in combination, are difficult to explain by natural processes alone. For example, on exoplanets, scientists are starting to consider technosignatures beyond just radio signals. These include industrial pollutants in atmospheres, such as chlorofluorocarbons, which are purely artificial, unnatural levels of greenhouse gases, or even waste heat. Applying this to Earth, we would then look for analogous signals in our geological record. Could ancient industrial pollution have left its mark in deep ocean sediments, perhaps as unusual concentrations of heavy metals or synthetic compounds? The question then becomes one of detectability after millions of years of dilution and transformation. The concept of planetary habitability itself gains new nuance. While we typically focus on the conditions necessary for life to arise and persist, comparative astrobiology, informed by the Silurian Hypothesis, asks, what conditions are necessary for a technological civilization to leave a lasting, detectable mark? A planet with intense geological activity might be great for life's evolution, but terrible for preserving the memory of its inhabitants. Conversely, a geologically quiet planet might preserve a more complete record, but perhaps be less dynamic in fostering complex life. This dramatic interplay between planetary dynamism and historical preservation is a key takeaway.
The very possibility of the Silurian Hypothesis, audacious as it sounds, stands on the shoulders of centuries of scientific discovery. Our ability to even ask such a question, to peer back into the dizzying depths of geological time, is a testament to several historical milestones in geology and paleontology. These intellectual achievements, a dramatic unfolding of human curiosity and ingenuity, have provided us with the conceptual framework and the analytical tools necessary to contemplate the existence of a truly lost society. One of the foundational milestones was the development of stratigraphy in the 17th and 18th centuries, most notably by Nicholas Steno. Steno's principles, the law of superposition, younger layers lie above older ones, the principle of original horizontality, sedimentary layers are initially deposited horizontally, and the principle of lateral continuity. Layers extend laterally until they thin out or are stopped by a barrier. These principles provided the bedrock for understanding the sequence of events in Earth's history. Before stratigraphy, the Earth's past was largely viewed through a biblical lens, measured in thousands of years. Steno's work allowed geologists to reconstruct chronological sequences of rock layers, providing the first true timeline for Earth. This was the first dramatic step towards deciphering the Earth's complex narrative. The 19th century brought the revolutionary concept of deep time, largely propelled by the work of James Hutton and Charles Lyell. Hutton, often considered the father of modern geology, articulated the principle of uniformitarianism. The present is the key to the past. This idea posited that the same slow, observable geological processes we see today, erosion, deposition, volcanism, have been operating over immense stretches of time to shape the Earth. Lyell popularized and expanded on this, arguing for a much older Earth than previously imagined, allowing for the incredibly slow processes of geological change to account for the Earth's features. This expansion of the perceived age of the Earth, from thousands to millions and eventually billions of years, was a dramatic paradigm shift, opening up the vast timeline where a primeval intelligence could theoretically exist.
These historical milestones represent a daring intellectual journey, each discovery building upon the last, gradually unveiling the complex, multi-layered story of our planet. The Silurian Hypothesis is a direct descendant of this legacy, a speculative yet scientifically grounded inquiry born from our deepest understanding of Earth's immense age and dynamic processes. It's a testament to humanity's relentless curiosity, forever pushing the boundaries of knowledge and always prepared for the dramatic unveiling of a hidden truth. The potential discovery of a primeval intelligence on Earth, while currently hypothetical, carries with it an unimaginable weight of cultural and societal impacts. This isn't just a scientific revelation, it's a profound existential shift, a dramatic redefinition of humanity's place in history and the cosmos. Imagine the headlines, the debates, the complete upheaval of established narratives. Such a discovery would resonate through every facet of human experience, leaving no cultural stone unturned. Firstly, the most immediate impact would be on our sense of human uniqueness. For millennia, many cultures and philosophies have placed humanity at the center of creation, seeing us as the apex of intelligence on Earth. Discovering that another technologically advanced species preceded us would profoundly challenge this anthropocentric view. It would be a humbling experience, forcing us to acknowledge that our reign might be just one chapter in a much longer, more complex planetary saga. The drama here is the shattering of deeply held beliefs, the unraveling of a cherished narrative.
This shift would ripple through religious and philosophical frameworks. Many creation myths and spiritual traditions posit humanity as a singular, divinely appointed creation. The existence of a prior intelligence would compel theologians and philosophers to reinterpret sacred texts and fundamental tenets. It could lead to new avenues of spiritual inquiry, questioning the nature of consciousness, sentience, and purpose in a universe potentially teeming with intelligent life, both past and present. The intellectual adventure would be as profound as the scientific one. Historical narratives would undergo a massive overhaul. Textbooks would need to be rewritten. Our understanding of geological epochs would gain an entirely new, potentially dramatic layer. The very concept of prehistory would expand to encompass an unimaginably ancient technological past. Archaeologists might suddenly find themselves looking not just for stone tools, but for subtle geochemical anomalies in deeply buried strata. This would ignite a global passion for deep-time exploration, transforming our historical quest into a cosmic detective story. The discovery would inevitably spark intense public debate and fascination. Science fiction, which has long explored themes of ancient alien civilizations, would suddenly feel less like fantasy and more like prescient speculation. Documentaries, books, and artworks would proliferate, grappling with the implications of such a find. There would be an explosion of public curiosity, fueling new generations of scientists, historians, and philosophers to explore the ramifications. The dramatic unveiling of such a secret would captivate the entire world.
Furthermore, the implications for environmentalism and sustainability would be immense. If the primeval intelligence perished due to environmental collapse, it would serve as the ultimate cautionary tale for our own Anthropocene era. It would underscore the fragility of planetary ecosystems and the potential for technological societies to inadvertently cause their own demise. This could galvanize global efforts to address climate change and environmental degradation, framing our current challenges not just as problems for our species, but as a test for any intelligent civilization on Earth. The drama here is the stark warning from the past. Economically, new scientific fields and industries would emerge, focused on deep-time exploration and the analysis of ancient technosignatures. Governments and international bodies might invest heavily in programs aimed at further investigating and understanding this lost civilization, leading to unprecedented levels of scientific collaboration. Ultimately, the cultural and societal impacts of discovering a primeval intelligence would be truly transformative. It would force humanity to look inward and outward with fresh eyes, to reconsider our arrogance, embrace humility, and perhaps to find a deeper, more profound connection to the ancient, living planet we call home. It would be an adventurous, dramatic journey of self-discovery, fueled by the echoes of a world long lost, but forever inscribed into the very fabric of Earth's mysterious past.
The pursuit of the Silurian hypothesis is not merely an exercise in speculative thought, it's a powerful driver for the development of future methods in geological and astrobiological research. If we are serious about looking for the subtle whispers of a primeval intelligence, we must push the boundaries of our current scientific capabilities, inventing new tools and refining existing techniques. This represents an exciting, adventurous frontier in science, where cutting-edge technology could unlock Earth's deepest, most dramatic secrets. One key area for advancement is ultra-high-resolution geochemical analysis. While we currently use isotopic analysis to detect shifts, future technologies could allow for even more precise measurements of trace elements, rare isotopes, and complex organic molecules in ancient sediments. Imagine instruments capable of detecting subtle, non-natural molecular structures or unusual elemental ratios at the parts per billion level, even after millions of years of degradation and dispersal. This would require advancements in mass spectrometry, atomic force microscopy, and perhaps entirely new forms of chemical spectroscopy designed to detect fossilized industrial waste. The drama lies in the precision required, akin to finding a single unique atom in a mountain of sand. Deep geological drilling will be crucial. While we have drilled deep boreholes for oil and gas and for scientific research, future efforts specifically targeting potential Silurian hypothesis evidence would need to be strategically planned. This might involve drilling into exceptionally well-preserved sedimentary basins that have remained tectonically stable for hundreds of millions of years, or into regions where ancient deep ocean sediments, which are less affected by erosion than land surfaces, have been uplifted and exposed. The logistical challenges and costs would be immense, but the potential scientific payoff could be revolutionary.
We also need to develop more sophisticated paleoclimate and paleoenvironmental models. To distinguish a technosignature from a natural geological event, we need incredibly detailed understanding of Earth's past climate dynamics, oceanic circulation, and atmospheric composition. Future models, perhaps leveraging artificial intelligence and vast data sets, could simulate natural variability with higher fidelity, allowing us to identify truly anomalous spikes or shifts that defy natural explanation. This would involve integrating data from multiple proxies, ice cores, sediment cores, fossil records, and geological structures to build a comprehensive picture of ancient Earth. The development of remote sensing techniques that can peer beneath the surface, specifically tailored for detecting ancient, deeply buried anomalies, could also be transformative. While ground-penetrating radar has limitations, perhaps future seismic imaging or gravitational anomaly detection techniques could be refined to identify unusual patterns in subsurface density or structure that might hint at large, buried artificial constructions, even if severely altered. This is highly speculative, as geological noise would be immense, but the adventure lies in pushing these boundaries.
Furthermore, the application of machine learning and artificial intelligence to geological datasets could be revolutionary. AI could be trained to identify subtle patterns and correlations in vast amounts of geochemical and geological data that are beyond human analytical capabilities. It could flag anomalies that we might otherwise overlook, identifying a signature that is not obvious to the human eye, but statistically significant. This would transform our search into a data-driven quest for hidden patterns. Finally, a truly interdisciplinary approach is paramount. Future research on the Silurian Hypothesis will require unprecedented collaboration between geologists, paleontologists, geochemists, astrobiologists, computer scientists, and even philosophers. This collective effort, pooling diverse expertise and perspectives, will be essential for both developing the necessary tools and interpreting any ambiguous findings. The dramatic unveiling of such a profound secret would require the concerted effort of the entire scientific community.
The Silurian Hypothesis, by posing such an extraordinary question, pushes the boundaries of scientific inquiry. It encourages us to imagine not just what we can find with current tools, but what we might be able to find with the tools of tomorrow. This forward-looking approach ensures that the quest for Earth's deepest secrets will continue to drive innovation, inspiring new generations of adventurers and scientists to unlock the mysteries buried beneath our feet, potentially revealing a past far more complex and dramatic than we ever dared to imagine. The future of scientific exploration, in part, lies in uncovering the echoes of the deep past.
Our journey through the speculative yet scientifically grounded landscape of the Silurian Hypothesis has taken us on an exhilarating quest to unearth Earth's hidden history, pushing the boundaries of what we thought possible. We've wrestled with the relentless forces of geological erasure, explored the tantalizing whispers of technosignatures in ancient strata, and grappled with the profound implications for humanity's place in cosmic time. This isn't just a scientific thought experiment, it's a dramatic exploration into the very nature of existence, a mystery that could redefine our understanding of intelligence, longevity, and our cosmic significance. The Silurian Hypothesis, pioneered by Gavin Schmidt and Adam Frank, forces us to confront the limitations of our current scientific toolkit when peering into the deep past. It's a humbling reminder that the absence of obvious archaeological evidence does not equate to the absence of a lost society. The Earth is a dynamic, living planet, constantly recycling its crust, eroding its mountains, and burying its history under layers of time. Any fleeting technological civilization, even one lasting for hundreds of thousands of years, would struggle to leave a clearly discernible mark for us to find millions of years later.
Yet the adventure lies in the search for the subtle, indirect clues, the isotopic anomalies, the unusual concentrations of rare elements, the unique chemical fingerprints that might persist through geological eons. It pushes us to refine our geochemical analyses, to develop more sophisticated models of Earth's ancient environments, and to think creatively about what truly constitutes a technosignature in deep time. This quest connects the geological history of our own planet with the grand astrobiological search for life and intelligence elsewhere in the cosmos, revealing that the challenges of detection are universal, whether looking across light years or across millions of years. Ultimately, the Silurian Hypothesis offers a profound philosophical reflection. If we are not the first, it means that intelligence and even technological capacity might be a recurring phenomenon in planetary evolution. This doesn't diminish humanity's achievements. Rather, it places us within a larger, more ancient narrative. It's a dramatic realization that could temper our arrogance, inspire greater humility, and ignite a deeper sense of responsibility towards our vibrant, ancient planet. Our current Anthropocene epoch is leaving an indelible mark. The thought of a vanished predecessor serves as a powerful cautionary tale, urging us to consider our legacy and strive for a more sustainable, enduring relationship with Earth.
The questions raised by the Silurian Hypothesis are far from settled. They're an invitation to continued scientific inquiry, to push the boundaries of our knowledge, and to look at the familiar world beneath our feet with new eyes. The potential to uncover an unwritten chapter of Earth's story, a lost epic of intelligence, is one of the most exciting and paradigm-shifting quests imaginable. It reminds us that the greatest mysteries often lie not in the distant stars, but right here, buried deep within the heart of our own extraordinary planet. The adventure continues. Subscribe to join us for more mind-bending mysteries and explorations into the hidden corners of science and history.